Good morning, ladies and gentlemen. May I have your attention, please? Thank you. I appreciate that. Let's go ahead and begin our discussion. Today we're going to continue solving quadratic equations, but we're going to meet a new friend. Yes, that's right. Several of you ran into difficulty when trying to solve number 4, and for good reason. Right? We encountered a situation that we haven't run into thus far this unit, and so we're going to talk about that today. But first, let's go ahead and remind ourselves about the different methods we have. So if there's just an x squared term, what's the best method to solve this quadratic equation? Caitlin? Absolutely. We can solve by taking square roots if there's just a single squaring term. So we go ahead and isolate the squaring term. It looks like the best first step would be to divide both sides by 3 in this case. That gets our squaring term alone. And then we can undo squaring by square rooting, so long as we consider both the positive and negative square root when undoing that even integer exponent. So it looks like x will be given by the positive and negative square root of whatever is there, in this case 16. Again, sometimes it'll reduce, sometimes it won't, but I saw many of you had 2 correct answers. It looks like x equals positive 4 and x equals negative 4. Raise your hand if you have both of those already, please. Plus or minus 4. Good job, you guys. So solving by taking square roots is certainly an efficient way to solve if I just have a single squaring term. All right. Number 2, can't solve by taking square roots, right? We can't solve that by taking square roots because we've got an x squared term and an x term mixed. And so what do? Well, we can try solving by factoring, right? We can try solving by factoring. And so if we were to do that, we could standard form everything on one side set equals 0. We could stop, think, GCF is their greatest common factor hiding inside of each of these terms. It looks to me like there is 2x squared plus 4x minus 6. So each of those terms has a 2 in it. We could factor out a 2. Now, you could still try factoring without taking out the GCF, but by factoring out that GCF first in a reverse distributive property problem, you chunk it down to smaller numbers and make it easier to factor. So I'm going to go ahead and recognize that there's a 2 inside of each of those terms, and factor that out of each term in a reverse distributive property problem as my first step. So let's go ahead and do that. X squared plus 2x minus 3 remains. And now I'll go ahead and focus in on that trinomial inside. I'll keep my 2 alone for the party. I'll fill in my variable for my first. It looks like x squared must come from x, and x as my firsts. And now I'll consider my factors of the last. My factors of the last, negative 3, include plus and minus 1 and 3. So I'll go ahead and try a placement of 1 and 3, and I'll consider the signs of my last. In my green trinomial, my last number, my last term was negative. So what does that tell me about the signs of my binomial? If my last number is negative, what does that tell me about the operations of my binomials? Will it be the same operation or opposite operation? Ian? Opposite. Opposite, good. So we need to go ahead and decide what placement will result in an outer and inner product that's sum to give me this positive 2x. It looks like minus 1 and plus 3. Does that create an outer and inner product and sums now to give me the positive 2? Awesome. So we've got fully factored form, set equal to 0. I can now utilize the 0 product property and set each individual factor equal to 0 and solve. Notice how this 2 is a factor, but it doesn't include a variable component. This 2 will never equal 0. So I don't have to set 2 equal to 0 and try and solve because there's no variable here. That doesn't equal 0, it equals 2. These are the only factors that will contribute to solution. So I'll go ahead and break it up. X minus 1, does that ever equal 0? X plus 3, does that ever equal 0? And solve separately. So it looks like x equals positive 1, x equals negative 3, and you could have gotten those, right? You could have gotten those by factoring without doing a GCF problem, but you still should have gotten the same solution. Raise your hand if you had x equals 1 and x equals negative 3 already. You did. Oh, good job. Okay. Nice work. So we can always check those in the original. I can plug in 1 and say 1 squared is 1 times 2 is 2, plus 4 times 1 is 4, 2 plus 4 is 6, 6 minus 6, that equals 0. I can do the same thing for negative 3. Negative 3 squared is 9 times 2 is 18, plus 4 times negative 3 is minus 12, 18 minus 12 is 6, 6 minus 6 does equal 0 too. So we've got both our solutions. So far, we've solved by taking the square root, we've solved by factoring, right? Now, let's go ahead and see what method might be best for number 3. So do I have multiple variable terms in number 3? Do I have multiple variable terms in number 3? Hans?
No.
No, I've got a single variable term, quantity squared. And so again, I'm going to solve by taking square roots. Don't FOIL that out, right? Don't rewrite that as x minus 4 times x minus 4 and multiply those two binomials together, right? Like we did to algebraically simplify expressions on our quiz. That's just going to make an x squared term and an x term, right? And a constant term. So you'd be creating more variable terms, whereas right now there's just a single variable term, quantity squared. So don't FOIL that out. Instead, you can use inverse operations to solve right now. So we'll go ahead and subtract 3 from both sides. That will get my quantity x minus 4 all squared alone on one side. And now that I've had my squaring term isolated, I can undo squaring by square rooting, just like we did with number 1. The only difference is there's parentheses here. So that gets rid of the parentheses, and I get x minus 4 is equal to positive and negative square root of 49. Sometimes that'll reduce, sometimes it won't, but either way we'll break it into two parts. One part is x minus 4 is equal to the positive square root of 49, that's 7. The other part is quantity x minus 4 is equal to the opposite of square root of 49, that's negative 7. And now we can solve separately. It looks like a one-stepper on both sides. I get x equals 11, or I get x equals negative 3. I'm going to go ahead and check that. I'm going to check that negative 3. So I'm going to plug that into my original. Let's see if that makes a true statement. Negative 3 in for x. Minus 4 is negative 7. Negative 7 quantity squared is positive 49. And 49 plus 3, does that equal 52? Yes, it does. And we can do the same thing for 11. Awesome. What questions do you guys have about number 3? Okay, and so the last one now is a springboard for our discussion. Do I have x squareds and x's mixed in the same problem? No. So do I have to solve by factoring or completing the square? No, we can solve by taking square roots. But when we do that, when we isolate the quadratic, by first subtracting 64 from both sides, I get x squared equals negative 64. And what happened when you try to solve that? Kaylin?
There was an error.
Yeah, there was an error, right? The error, what's the error? Well, there's no real number such that when squared, right, multiplied by itself, results in a negative, negative 64. Wait a minute. We're now negative 8. Does the negative 8 work? Negative 8 times negative 8? No, that would be positive 64 as well. And so there's no real solution. There's no real solution to number 4. And yet, there are solutions to that quadratic equation. There are solutions, in fact, variable values for x that when substituted in the original and worked out make a true statement. And so today, we're going to pin down how it is that we find those complex solutions that include imaginary components. We're going to solve quadratics today that have non-real answers and determine how we represent that. It turns out that a variety of real-world applications include these complex numbers with non-real components, what we call imaginary components. And in fact, we get our own designation for the square root of negative 1, and that's what we're going to investigate today. And we're also going to see some applications of complex numbers with non-real components in real-life applications. So that's pretty neat. All right, so we're going to pause this. We'll see it again. Let's go ahead and stop the recording at the same time, and we'll take care of our homework check, and then we'll get your quizzes back to you so you can see exactly how you did. Then we'll resume the recording. Okay, ladies and gentlemen, so a gentle reminder, if you are going to apply for the compacted course, the FST/Pre-Calc compacted course, that your applications, which you can pick up during the mandatory informational meeting, right, during contact time this week, whether it's Mr. Notsky tomorrow, or whether you already went today to Mr. Marks, you must turn in that application paperwork on Monday the 15th. All right, so what are we doing today? Today we're going to solve quadratic equations, even those that include non-real solutions. So we're going to investigate complex numbers that include imaginary components. We're going to find non-real solutions to quadratic equations, and we're going to be able to solve ones like number 4. We'll also perform operations with complex numbers, and the good news is that we can treat these expressions a lot like we can treat variable expressions with x. So all your things that we've learned about foiling or combining like terms are still going to hold true with our new imaginary unit I. Okay, so Bellwork number 4 wasn't a real number because every real number squared was positive, and we talked about that before. So how do we solve x squared equals negative 64? Well, it turns out that guess what? This exponent 2 still tells me that I should have 2 solutions to this quadratic equation. And in fact, we do have 2 solutions to this quadratic equation. It's just that they are non-real solutions. They're complex numbers that include imaginary components, and they're non-real solutions. Nevertheless, when substituted into the equation for x and worked out, they create a true statement, and so they are solutions all the same. We need to expand our number system to provide a solution. So we use an imaginary number. That's called I. Right? I is going to represent the square root of negative 1. So when we were trying to solve this, we undid squaring by square rooting, and we got x equals the positive and negative square root of negative 64. If we entered that in our calculator, we would get an error, non-real answer. However, there is a solution. It's just non-real. We're going to get around this fact by calling the square root of negative 1, this little negative inside of my square root, that's going to be I. So I will be defined to be the square root of negative 1. We can now rewrite this as plus or minus square root of negative 1 times 64. You agree that negative 64 is negative 1 times 64? And this negative 1 inside of a square root is now going to be called I. And so we'll handle the 64 the same way we always have. The square root of 64 is 8. And the square root of negative 1 is I. Therefore, I have 2 answers. One of them is 8i, and the other one is negative 8i. We still do a plus or minus outside. That still gives us 2 solutions. If there were a negative inside, it just corresponds now to an I outside of the radical. And we're going to do this. We're going to do this several different times today. If I equals the square root of negative 1, then I squared would be the square root of negative 1 times the square root of negative 1. Well, the square root of negative 1 times itself, right? A squaring undoes the square root, and we get what's inside. So what's inside? Negative 1. We'll also be using this today. So I squared equals negative 1. So we need to remember 2 big things today when we perform operations with complex numbers. Firstly, I is equal to the square root of negative 1. It's called our imaginary unit I. Anytime we see a negative inside of a square root, it's equivalent to an I out front. Secondly, I squared, right, is equal to negative 1. And that's going to help us when we perform operations with complex numbers as well. Let's go ahead and take a look now at some equations that up until now we were unable to solve. Guess what? Now we will be able to solve these and get 2 solutions. So if x squared equals negative 4, we can undo squaring by considering the positive and negative square root. This means that x would be given by the positive and negative square root of negative 4. We won't do this every time, but it's useful to see that that negative 4 is just negative 1 times 4. We can now handle this, right? We can now handle this as two separate quantities. I know that a negative 1 inside of a square root we can now handle. We'll call that I. I also know that a 4 inside of a square root is equivalent to an integer out front. Typically, we write the coefficient in front of the imaginary unit, so I get 2 solutions. X equals positive 2i, and x equals negative 2i. I can solve equations like 2x squared equals negative 72. What do? Well, we still solve by taking square roots, just like Bellwork. Because there's only a squaring term, I would divide both sides by 2 as the best first step. That gives my quadratic x squared alone. That's equal to negative 36. And what undoes squaring? Square rooting. So if x squared equals negative 36, then x is given by the positive and negative square root of negative 36. it just so happens that now we're able to simplify this, right? Isn't negative 36 equal to 36 times a negative 1? And a 36 inside a square root is equivalent to a 6 out front, and a negative 1 inside a square root is equivalent to I out front, which means I have two answers. I get x equals 6i, and x equals negative 6i. Now, wait a minute. I thought that if we generated a solution to an equation, regardless of type, that when substituted into the original expression and worked out, it makes a true statement. So I'm going to go ahead and check and see if this 6i, when substituted into my original, makes a true statement. So how would I do that? Well, I'll go up to my x, and I'll replace it with 6i, and I'll see if it equals question marks negative 72, right? So let's go ahead and check the 6i into the original. We'll rewrite the original, but everywhere I see an x, I'm going to put what? I'm going to put 6i. We're going to see if that equals question mark negative 72. So here we go. 2 times, and 6i squared would be 6i times 6i. That would be 36i squared. Does that equal question mark negative 72? Well, let's see. I know that 36, right, I squared is equivalent to 36 times negative 1, because I squared is negative 1. Therefore, 2 times 36 times negative 1 equals negative 72. And so we verified that 6i is in fact a solution to the original quadratic equation, and the same is true for all of these. And so we can go ahead and box these. That's pretty sweet. Now we'll be able to find two solutions for any quadratic equation, except in the special case where my vertex lies on the x-axis and I have a single x-intercept. Let's go ahead now and remind ourselves about where this imaginary component I fits into our real number system. And so we've been working with complex numbers all year long. It's just that our complex numbers so far have included an imaginary component, right, of 0. And so we haven't included I in our answers yet. All of our real numbers, right, have included just the real component A. So we've been working with whole numbers, right, like 0, 1, 2, 17. We've been working with integers, right? We've been working with integers like negative 4. We've been working with rational numbers like 2/3 and square root of 25. We've been working with irrational numbers like the square root of 26 and pi. And we've been working with all these numbers which are real. However, real numbers are just a subset of complex numbers. Real numbers are complex numbers. It's just that the real numbers we've been working with didn't include an imaginary component. Once we include this imaginary component, I, suddenly we open up a whole new realm of possibilities. That's what enables us to solve those quadratic equations like x squared equals negative 64. We can now solve that and get solutions. Solutions such that when substituted in, result in true statements. And so that's why we need to consider these complex numbers with imaginary components, because they are in fact solutions to the original equation. So I is equal to the square root of negative 1. You guys need to remember that I squared is equal to square root of negative 1 squared, which equals negative 1. So anytime we're simplifying, I squared is always going to be equal to negative 1. And that's a big idea. Pure imaginary are complex numbers where the real part, A, is 0. So these would be numbers like our solutions we got to that first one, 8i and negative 3i. Those are where is that in blue? 8i, negative 3i, those imaginary numbers, right? Those complex numbers with no real part, those are pure imaginary. let's go ahead then and practice some operations. Operations with pure imaginary numbers are easy. The commutative, associative, distributive properties of addition and multiplication are true for all imaginary numbers. Consequently, the operations are predictable. What? It means that we can combine like terms. I terms will combine with other I terms, much as if we treat it with a variable. But it's not a variable. I is a number. It's the square root of -1. In any case, it'll be easy to simplify. 7i minus 3i plus 5i. We simply add or subtract as we would if it were a variable. So here we go. 7i minus 3i is 4i plus 5i is 9i. It's that easy. We'll simply add or subtract like terms from left to right. If I see a negative inside of a square root, I know that's equivalent to an I out front. So I'll handle this number 4 inside the square root as I always have. That would be equivalent to 2. But when I have a negative inside, I must now include an I outside. So this becomes 3 times 2i. The 4 inside produced this 2. The -1 inside produced this I. So to rewrite that square root of -4, it's equivalent to 2i. Minus 2 times, and now let's simplify the square root of -25. What's the square root of 25? 5. What's the square root of the -1 inside? I. So our square root of -25 is changed into 5i. Our square root of -4 is changed into 2i. All right. Well, that means this is equivalent to 6i minus 10i. 6i minus 10i, are those like terms? Yes, they are. So we can combine them and get -4i. That's it. We can also multiply imaginary numbers. 3i times 5i is, you guessed it, 15i squared. However, to be in standard form, our largest I power is I to the first. I must rewrite an I squared anytime I see it and replace it with -1 because I squared is equivalent to -1. So number 12 isn't finished. That's okay. What's I squared equivalent to? -1 times the 15 out front is -15. So 15i squared is equal to -15. Number 13, we want to make sure that we simplify our radicals first. And so we're going to go ahead and rewrite this first radical in red. The square root of -16 is the same as the square root of 4 times the square root of -1. That's, I'm sorry, the square root of 16 times the square root of -1. That's 4i. Times the square root of -49 is equivalent to 7i. 4i times 7i is 28i squared. But we're only allowed to write numbers, real numbers or I. We can't have I squared, so what's I squared equivalent to? -1, which means my final answer is -28. Number 14, guess what? If I can multiply imaginary component numbers, I can also divide them. 18i divided by 3i is, you guessed it, 6. It's that easy. Number 15, we'll simplify first. Square root of -144 is simply 12i. Over the square root of 81 is, sorry, the square root of -81 is 9i. And now we can simplify that as we always have. 12 divided by 9 would be 4/3. It's interesting to point out here that while we're performing these operations with imaginary numbers, some of them pure imaginary. Many of our results are real numbers, even rational or whole numbers. And so that begins to give you a glimpse as to why we need to be able to work with imaginary numbers, because they represent real, right? They represent real results. Oftentimes, they're solutions to real-world applications. So we have to be able to manipulate expressions that involve imaginary numbers. Let's go ahead and continue on. We've got 16 combined like terms on top. Reduce second. So it looks like we can combine like terms on top first. 17i minus 12i is 5i. Then divide it by 10i and get 1/2. Number 17, rewrite your square roots first in terms of I and then continue on. So my first step would rewrite the square root of negative 16 as 4i. The square root of negative 9 as 3i. That's still all over 5. Combine like terms on top. 4i plus 3i is 7i. And then we'll go ahead and rewrite that in standard form. That would be 7/5 I. And we'll talk about that soon. That would be 7/5 I is my final answer. So look how many of these ended up being real numbers. Even though we were performing operations with complex numbers, look how many end up being real numbers. Negative 15, 6, 1/2, 4/3, negative 28. And then several ended up staying imaginary. Awesome. What questions do you guys have about the manipulations? So we need to have the manipulation so that we can do things. That is, solve quadratic equations and use imaginary numbers when we're working on real-life application problems. And so the big idea is that complex numbers in standard form are of the form a plus bi, where a is the real part and bi is the imaginary part. I is equivalent to the square root of negative 1. So anytime we see a negative inside of a square root, it's going to be equivalent to an I out front. Some books call bi the imaginary part, and that's what I'm used to seeing. Bi is the imaginary part, and then a is the real part. A plus bi and c plus di are equal complex numbers if and only if the real parts are equal and their imaginary parts are equal. And so we've got this kind of one-to-one property, kind of like we did with logarithms back in semester 1 for exponentials. All right, let's go ahead and do some stuff then. Let's go ahead and perform our operations with complex numbers. And most of these operations, right, are the same as if they were polynomials. So let's simplify and remember, anytime we see an I squared, we've got to change that back into a negative 1. So here we go. We can add or subtract like terms first by getting rid of the parentheses. It looks like that plus out front. If I were to distribute a plus 1 through the parentheses and rewrite without parentheses, I'd keep the negative on the 5, I'd keep the negative on the 6i. Now we'll go ahead and combine like terms. What? Yes, like terms. This 3 and this negative 5 are both real number components of the imaginary, of the complex number, so I'll combine them and get negative 2. The 2i and the negative 6i are both the imaginary components of the complex number, so I can combine those and get 2i minus 6i is minus 4i, which is why my final answer is simply negative 2 minus 4i. That's in standard form because it's a, the real part, plus bi, the imaginary part, in that order. So that's standard form and that's done. If we wanted to subtract complex numbers, we could do so as well, but first we have to get rid of the parentheses. In this case, I would treat that negative in between the parentheses as a negative 1 and distribute it through that second parentheses to rewrite. So I get 1 minus 6i, but now I get minus 4 minus 7i as I distribute it. Combining like terms, 1 minus 4 results in negative 3 for my real part. Negative 6i minus 7i is minus 13i for my imaginary part, which means my final answer is just negative 3 minus 13i. Notice how this is standard form. We've got a plus bi. So we've got real part plus or minus the imaginary part. Awesome. Not only can we add or subtract complex numbers, we can also multiply complex numbers. And we're going to do that as if they were polynomials as well. Let's go ahead and FOIL this bad boy. So we'll go ahead and remember that we can multiply first times first, right, to result in the first product, f. 2 times negative 3 is negative 6. We can multiply the outside terms in order to get my outside product. So 2 times negative 5i would be negative 10i. We can multiply 3i times negative 3 to get my inside term. That would be negative 9i. And for L, we can do 3i times negative 5i is negative 15i squared. So we can multiply two complex numbers in standard form together, just like we would as if they were polynomials. Right? We FOILed out. Now let's combine like terms. We know that the I terms can be combined through addition or subtraction, and anytime we see an I squared, that's equivalent to negative 1. So we must change that into a negative 1 anytime we see an I squared before simplifying completely. So I would get negative 6, combine like terms, minus 19i, and then if I squared is negative 1, what's negative 15i squared? Well, it would be plus 15, which makes our final answer negative 6 plus 15 is 9 minus 19i. Again, notice how all our answers then are in standard form, a plus or minus bi. They're all standard form for complex numbers. Real component first, followed by imaginary component, if any. All right, let's go ahead and do number 4 then. So you guys go ahead and FOIL that out. For number 4, we're going to go ahead and multiply first, outside, inside, last. 2 times 2 is 4. Outside, 2 times negative 3i is minus 6i. Inside, 3i times 2 is plus 6i. And last, 3i times negative 3i is minus 9i squared. Watch what happens when we combine like terms here, you guys. Negative 6i plus 6i. The i's, right, sum to 0. And I'm left with 4 minus 9i squared. Is this in standard form? Is it ready to box? No. I can only have I to the first power. Right now I have I to the second. That's okay. What is I squared equivalent to? Chrissy?
It's negative.
Absolutely. This I squared is equivalent to negative 1. So I can rewrite this as, guess what? A single real number. No imaginary component. This negative 9 times negative 1 is plus 9. So I get 4 plus 9, which is 13. Again, this gives us some insight as to why we need to be able to work with imaginary component complex numbers, because sometimes the solutions to real-world problems involve complex numbers with imaginary components, and the results end up being real. If we multiply that special pair together, we got a real number. So the result was a real number only. This pattern of multiplying a plus bi times a minus bi is called complex conjugates. And we saw that. We'll see that again in FST when we simplify radical expressions. And again in pre-calculus when we divide complex numbers. In the meantime, however, let's look at an application of complex numbers in the real world. And so, a variety of real-world applications include complex number systems with imaginary components. And so when we're talking about fluid flow, the way that air moves around a car, the way that an airfoil is constructed to maximize the lift for a wing of an airplane, it depends on the solutions with complex numbers that involve imaginary components. One application to electricity is the measure of impedance. And so electrical impedance Z is defined as a complex number, which includes voltage and current. Remember voltage, right? When you go in and you plug in your hairdryer in at home, right, into a 110 circuit, 110 volts, voltage refers kind of to the electric potential that a given circuit has. The higher your voltage number, sort of the greater potential that a circuit has to do work, okay? And so we've got voltage is a measure kind of how powerful a particular circuit or appliance is, and then current I is aptly named. Current I is a measure of really how many electrons are flowing through the circuit. And so current, you can think of how much electricity is moving through the circuit or the wires. A complex number representing impedance is of the form Z equals V plus I, where big I is the current and little I is our imaginary unit, the square root of -1. The total impedance, Z sub t, of a circuit made from two connected circuits is a function of the impedances Z sub 1 and Z sub 2 of the individual circuits. The two electrical circuits may be connected in series or in parallel. And so I think about a circuit in series versus in parallel is kind of like when you open up the flashlight batteries to change out the flashlight batteries, and you put one end to end, right? End to end. That's a circuit that's connected in series. And so when you think about putting those batteries in your flashlight end to end, touching and making a chain, that's a series in series, a circuit in series. Versus in parallel, that would be like when you open up your graphing calculator, the back battery panel, and they're alternating, one's this way, then this way, then this way, right? That's a good way to think about kind of the parallel circuits. In any case, let's go ahead and use these formulas to calculate total impedance so that we can practice now working with complex numbers. And so in a series circuit, total impedance Z is given by the sum of the individual impedances. In a parallel circuit, then the total impedance is given by this formula, the product of the individual impedances, then divided by the sum. So let's go ahead and suppose we had two electrical circuits. Let's practice our operations with complex numbers. First, in series, let's calculate the total impedance. And so all we're going to do is use the formula. In order to get Z sub t, the total impedance of the circuit in series, it appears as though we simply add our Z sub 1 plus our Z sub 2. So in series, we would add 4 plus 2i plus 5 minus 2i. So it looks like in series, I'm going to just make a little space. You guys don't mind. It looks like in series, all we need to do is add these, and so that's pretty easy. We'll add our real component, we get 9, and we'll add our imaginary component. Well, look at that. Looks like we get 9. Did you guys get 9? That's pretty sweet. So notice how we had impedances of my individual circuits, and when we connected them, the total impedance ended up being a real number. Now let's consider calculation of the total impedance, but now using a circuit where we connected the individual circuits in parallel. So how are we going to do that? Well, now we'll do the product of the two numbers. So the product of the two numbers would be given by 4 plus 2i times 5 minus 2i. There's my product, Z sub 1 times Z sub 2, all over, and the bottom's easier. The bottom is just that sum, Z sub 1 plus Z sub 2. Well, we already did that, didn't we? That was the 4 plus 2i plus 5 minus 2i. Let's go ahead and see how that goes. So we've got 4 plus 2i times 5 minus 2i. That is a job for FOIL. So we'll do first, outside, inside, last. I'll go ahead and stick with my same color coding. 4 times 5 is 20. My outside product, 4 times negative 2i is minus 8i. Listen, Mr. Prince. I'll send them down. You're welcome. Joe, it looks like you're up next. Guidance. And the I then would be my inside product. 2i times 5 is plus 10i. And my last would be 2i times negative 2i. Watch what happens here. Negative 4i I squared. So as Chrissy pointed out before, we can simplify this further. I squared is equivalent to -1, and we'll be able to keep going. This is still all over the sum of my individual impedances. Well, we already did that. Then we already do 2i minus 2i is 0 i's, and 4 plus 5 is 9. So my intermediate step looks like that. Now we'll go ahead and combine like terms. Negative 8i plus 10i is plus 2i, so I get 20 plus 2i. And then remember, I squared is equivalent to -1. So negative 4i squared is -4 times -1 is plus 4. That's still all over 9. And guys, we're almost there. Hang tight. 20 plus 4 is 24 plus 2i. That's all over 9. And lastly, we'll split up into a plus bi. So I'll split this up as 24/9 plus 2/9 I. Notice that we've rewritten this in standard form, a plus bi. Awesome. I'm going to go ahead and box this. And we're set. It was our hope that by looking at a real-world example with electrical engineering, we could see how imaginary numbers can be used in real life. So let's go ahead and say hello to our little friend. Oh, how cute. He has an imaginary friend. I love math jokes. That's pretty sweet. All right. So I want a written response from everybody, please, and then be ready to share. And it looks like we will get a little bit of work done. Awesome. But first, let's go ahead and bring it together for closure. So what does the number I equal? Go ahead and write down the response. Don't say it out loud. What then does the number I squared equal? What are the solutions to k squared equals -16? And keep in mind there should be two. There should be two solutions to a quadratic equation k squared. And then what are imaginary numbers good for? Who needs them? Why do we spend time in class talking about imaginary numbers? Okay, what does the number I equal? So what is I equivalent to? Aaron?
Square root of -1.
Good. I equals the square root of -1. Raise your hand if you have the same as Aaron. The square root of -1. Good. So then what would I squared be equivalent to? Go ahead and tell the class when I call your name. Hannah? -1. Good. So anytime you're performing an operation with complex numbers and you generate an I squared in your expression, you need to change that with -1 before continuing to simplify. Nice job. Thank you. What are the solutions to k squared equals -16? Well, I would find those by taking the square root of both sides, the positive negative square root of -16, but now I have a means for simplifying that. Isn't that equal to the positive negative square root of 16 times -1 inside? And my 16 inside is equivalent to a 4 outside, just like my -1 inside is equivalent to I outside. So I get two answers. One is k equals 4i. The other answer is k equals -4i. Still two answers to a quadratic equation. It's just now they have imaginary components. And lastly, imaginary numbers are good for a variety of real-world applications, including but not limited to electrical engineering, fluid dynamics, physics, aeronautics, and their solutions to quadratic equations. So while these imaginary numbers, right, do include a negative inside of a square root, they end up being solutions to the original quadratic equation. When plugged in and worked out, they make a true statement. You guys did great today. In fact, you have a chance to get started on your assignment. I'm going to pause the recording and upload it to Moodle. You may use this time to get going on your assignment.